It's fine. Any thoughts which are coming to your head? So you want to minimize log 1 over p, which is equivalent to what? Maximizing your p of z hat, right? When is p of z hat maximized? It's like a Gaussian. It's Gaussian like latent variables, right? So when is p of z hat maximized? Exactly, like, let's make it like, so when z hat is 0, at that point you have the maximum probability. You have a probability distribution model which assumes maximum probability for z hat equals to 0, right? So if I didn't have this distortion term, and I just try to minimize this log 1 over p, and if I do a good job at minimizing this, all of my z hats will look like zeros, right? But now you know that's a very bad, what's the issue? Why don't I do that always? In practice, why don't I always do that? Exactly. So as one student answer, like if z hat is always 0, you'll lose all the information. That's like transmitting maybe something like just the DC value, right? So if all your variables z hat are 0, your decoder can't really do anything. It has nothing to go on forward with, right? So at that point, it's like completely lossy. You are basically sending a static value. Okay? And so why doesn't our machine learning model actually do that? Okay. Again, so the incentive really here for our machine learning compressor is to spread out z hat, right? So if I just keep my z hat at the exact same 0, I'm doomed, right? Like my rate would be 0. I don't have to transmit anything. The reconstructor can just recover 0, but it will get a completely lossy image, right? So I have to spread out. I have to give other symbols z hat so that my decoder can do something meaningful. And this term in the loss function is basically ensuring that you do that, right? So there is also a penalty you pay based on the distortion between image and image hat, right? So if you had a non-zero lambda, if this term exists, you are trading off. You are not really reducing just the one term. Reducing this term would try to push everything towards 0, but this term would say, no, my distortion loss will become very high. And so I wouldn't really want to do that. So essentially, based on this value of lambda, whatever it might be, you are trying to figure out how should I trade off my rate with distortion, really. Okay? Is this point clear? This is probably one of the confusing points of what's happening. So let me just summarize again. What we did in this whole pipeline is there were two issues. A, my quantizer was a discrete operation. Second, I had a basically table over which I was optimizing, right? Like log 1 over p of z hat is a table. The way we work around this, workaround 1 was okay. For quantizer, I can just do a straight through backward pass, and while forward, I can just add some noise. For my probability table, I said I'll assume some distribution, which I can backpropagate from. And then my encoder decoder will try to output z hats, which have roughly similar distribution. And the way we do this trade-off is by this rate and distortion term automatically figures out this trade-off on like how much z hat you want to be spread versus concentrated. Okay? So, any questions? Otherwise, let's just, so this notebook will post on the website. It's also on the lecture slide, but let's just do a live demo of Lund compression. While I'm starting to run this, it will take a little bit. So, anyone has any questions so far? Do we understand the basic idea? Yeah.
We could also optimize over how we are quantizing, right?
Yes. So that's actually, yes, we can. But we are not doing that. So there are various ways you can do that. I'm not sure what you have in your mind. Do you mean like various discrete options for quantization? Yeah, you can now bring reinforcement learning, do all that. Actually, Some of the recent works, that's what they have done, like there is mu0. So there they, for example, tried to introduce some reinforcement learning to do rate distortion sort of trade-off. And the idea was not change the quantization, but roughly like that, where you were playing with different losses, discrete loss options, and then you figure out which discrete loss option to pick. Because another way you can think of it is like, it's actually very interesting. There are lots of things you can play with because, okay, one idea could be you have images which is consisting of various blocks. Why am I quantizing it using the same quantization matrix, right? Maybe I can do different rate distortion trade-off per block. And overall, that will give me a better image because, okay, some blocks are just consistent, others have a lot of different things happening, so I can do that smartly. I think that was one part of what they did. And you can play a lots of such tricks, but it becomes as, if you have experience with RL, it becomes very computationally intensive very fast. But yeah, that's a fair idea too. Okay, any other questions? No? Cool. So then let's go over this notebook. So here we are gonna build a learned compressor for MNIST digits. So this is just an example from the data set. And we are gonna do exactly what we talked about in the class. We'll just go over each cell. So first we make this encoder and decoder transform. Sometimes these encoder and decoder transforms are also called analysis and synthesis transforms. The idea is this is like, okay. The idea is this encoder is like doing some analysis over the image and giving you this latents, and your decoder is doing synthesis of the image from these bottleneck layers. So this is just another term for the same layers. Here all we are doing is like, so again, if you've done machine learning, you would appreciate it. If not, it's okay. Just we are gonna show it in live code. So here you are just defining your analysis and synthesis transform as some layers using Keras. So our analysis transform is just some convolutional layers. Don't worry about it if you haven't heard of it. If you have heard of it, that's what we have. And then we have some non-linearities, which are leaky ReLU in our case. And so what this analysis transform needs to do though is start from the size of image and finally give you some latent dimensions number of vectors, which is hopefully much more small in number than the image dimensions. That's the really important thing. And then your synthesis transform starts with a dimension which is roughly of like this latent dimension, and then does like upsampling in our case. So that's being done through this conv2D transpose in our case. And that's basically the architecture for your analysis and synthesis transform. So you can also look at what these layers look like. Again, so you have some output shape, some number of parameters. Similarly for synthesis transform, you have that. So in our case, we have a total of 1 million trainable parameters. So you are tuning 1 million different values. Theta is 1 million dimensional, okay, which you are going to be tuning based on this data, trying to optimize for rate distortion. Then we do some like standard image stuff, which if you have started working on homework 4, you would have seen similar transform. You need to be careful about how you are treating images. Okay, so here let's just look at what an untrained network looks like. So right now we haven't done any training, we just pre-process the image. We apply the analysis transform to get this Y, and then we use this Y to get X tilde. So this is like our autoencoder kind of step, right? Exactly that. And then we optimize for L1 loss, you can do L2 loss, you can do many different things. That's not the point of this lecture, but let's say we work with L1 loss. And so this is what your original image looks like, and this is what your reconstructed look like. Like no surprises. Right now we haven't really trained this. We just have some random values for this encoder decoder. Like why would you even expect the X hat to come out to be same? Okay. Now, what we are going to do is we are going to define a loss function. Okay. So remember so we have to determine some log 1 over P of Z hat. That was our estimated rate loss. And the way we did it was like some prior distribution Z hat plus 0.5 minus prior distribution CDF Z hat minus 0.5. So this function. So go home and look at it. I'm not going to do each line, but basically we are doing exactly same what we have discussed in this notebook. Nothing more fancier. Our MNIST compression trainer basically now takes care of these two workarounds during training, which we talked about. So now we first pre-process the image, then we do this analysis, transform, or encoding. Then we add noise, right? So this is to take care of the quantization step. And your y tilde, like, which is an approximation of your compressed latence, is just y plus noise. And then your second workaround was this figuring out log 1 over p of z hat, right? So, So your workaround 1 was just recall, just adding some noise. This is exactly what this step does. You just added some uniform random noise. And then your workaround 2 was to represent your probability distribution as this CDFA minus B, right? And this is what our estimated rate loss is actually doing, right? It's basically just computing probability as differentiation of two CDFs, and then it's computing the negative log probability. Okay. And this basically gives you the rate loss. And then you can also find the X tilde, like recovered X, reconstructed X, right? Which is just the synthesis transform over your approximation of quantized variables, which is again, so you got the Z hat after adding noise, which is Y hat in the notebook. Sorry, we should have kept the notation same. And then from the Z hat, you can apply the synthesis transform to recover the original image I hat. This is what this step does. And your final loss basically consists of both the rate loss and the distortion loss. And our distortion loss is just original image X minus X tilde. Okay. And so now we can just like see if this works. We can apply this trainer to something to get some values of rate distortion. And so in the next step, let's just go ahead and train it. Let's just like backpropagate our variables, take gradients, try to learn these million parameters, which optimizes for rate distortion. Here I'm taking lambda to be 2000 and my latent dimensions to be just 50. Okay, so MNIST is a data set with 28 by 28 images. So from 28 by 28 dimension variable, we are just converting into some 50 dimension variable. And so it's training live, so you can see. So something which you see is that overall loss is going down, which is a good sign. So we want the loss to reduce at each of these iteration. So that's good. But if you see, I don't know, let's say rate loss. If you see rate loss actually increased first, right? But that's not a loss, right? Because we are not just optimizing for rate. We are optimizing for rate plus lambda D, and for this particular value of lambda, I might be trading off my rate and distortion. I'm more focused on maybe distortion from the starting point than the initial point. We are basically trading off both these. Okay, so this is training live. So let it finish. We'll just take a minute more. So while it finishes, so what's the next step, right? So this is all of this we did for training. Correct? But after we have actually trained, we'll just go back and apply a normal pipeline, right? Which is this. So we'll have the encoder, we'll quantize it, we'll have some Z hat, we'll assume it has this probability distribution P of Z hat, and actually use an arithmetic encoder. So all of this was to find the weights, encoder, decoder, but finally our compressor needs to come back and actually use some a real lossless compressor, right? And so that's exactly what we are gonna do next. So at this point, yeah, so we are just running it for 15 epochs, not doing anything fancy. It's finished running. So the next step is basically to actually implement my compressor. And my compressor here, we basically use the AEC compressor. So if you looked into the code from homework 3, I guess problem 4, you probably know what this is, but even otherwise, we have looked at arithmetic entropy coder. So this is just the implementation from SCL. So this is a context adaptive encoder, but here we are not really adapting the context. We are just looking at the encoder from the image. Okay. So now let's use an actual compressor and see the performance. So now we can define some encoder and decoder, and use this to actually encode and decode images. So the first thing which you see is like okay, this is what the frequency dictionary looks like when you actually encoded some images from what do I want to say? Yeah, so this is your actual frequency dictionary from the empirically encoded images. So this is the actual distribution of Z hat which you got when you worked with this encoder and decoder, right? And there should be a plot below, I think. Let's see, where is that? Okay. Sorry, I think I might have removed it in the end. Okay, never mind. So basically, if you look at this plot, right? Now you can see this has roughly what we expected to see, right? Like, so 0, most of the output latent variables, Z hat, actually peaked at 0. And then you have this fall down kind of criteria. So basically here, this is what the actual my P of Z hat looks like. Okay, and it roughly looks like what we might have hoped to be Gaussian. The second thing which you see is that if you look at the final rate and estimated rate, they are very close. So final rate is when you actually apply an entropy encoder on whatever discrete symbols you got. Your estimated rate is just the log 1 over P of Z hat, where we had an assumed probability model, right? So this is a good sign. It basically says again, like, our arithmetic encoder is doing the right job. Like, it's roughly compressing things to actually you can be more rigorous about this. We know that an arithmetic entropy encoder stays within 2 bits of overhead. And if you look at this final rate and estimated rate, you would see like, okay, they are always almost within 2 bits, right? So, okay, our arithmetic encoder did the correct job. And so at this point, okay, we can actually look at the reconstructed images and what the original images are. So on the left here, what we are showing is the original image X, and on the right is the reconstructed image X hat using this learned compressor. Okay. And so for example here, just using 89 bits, you start with this 5 and you get this reconstruction 5. And so overall, this compressor doesn't look bad. We literally class right now, and it's doing somewhat reasonable job. These are again 28 by 28, so quite 900 dimensional images like bits, and black and white, so just 28 by 28, which is roughly like 900 bits, something like approximately 90 bits. We have come up with a learned compressor which reconstructs most like the original. So pretty cool, right? And we didn't have to worry about like figuring out all the designing all the hand-tuned parameters for this particular one. We figured out the exact transform. You didn't have to know about, oh, there exists something called DCT and so on and so forth. If you had this technology and everything before, you would have probably rediscovered DCT using something like this. So that's pretty cool. So the next thing which I just want to show you, oh yeah, so here is the plot. Okay, I thought I had it above, sorry. Okay, so this is again the same plot which we kind of looked at in the lecture, right? So this thing, but just to show you guys again, here the blue curve is the standard normal PDF, okay? The red is basically the quantized PDF values. So this is like what your model suggests. So this is just the CDF of Z hat plus 0.5 and Z hat minus 0.5, okay? So the red points are same as the blue dots here. This is what we expect our model to be. And green is actually the empirical probabilities. So remember this Z hat table which I was showing you for different values of Z hat. This is like exactly these values, green ones. So you can see the green is not exactly same as red, but it's roughly following the red kind of architecture, right? And so it's roughly Gaussian. And there is a trade-off between what distortion and all those things, which will actually determine the empirical distribution compared to actual. The final thing which I want to show is this, like if you increase the lambda, okay, this is interesting. So what do you think happens when you increase the lambda? So how do you actually do the rate distortion trade-off, right? So we have trained a compressor. Actually, this is a one tricky point about the ML-based compressors or learned compressors. So we have trained our compressors which work really well for a given value of lambda. It trades off rate and distortion very well when I fixed what should be my trade-off. But you can imagine if I change my value of lambda, my learned weights will be different and they might value rate more or distortion more, which is something, a knob which we always want in lossy compression, right? So in our case, it's lambda. So let's say here, earlier the curves were with lambda 2000. Now let's say I reduce lambda to 500. And I am optimizing for rate plus lambda times distortion. What do you expect? Do you expect your reconstructions to be more lossy or less lossy? Okay, I hear more lossy. How many of you think it's going to be more lossy? How many of you think it's going to be less lossy? Cool. I think everyone almost said more lossy and some people are probably not sure. Yes, exactly. It's going to be more lossy, right? Because now you're putting less weight to distortion. You're reducing lambda. So in your loss function, you're putting less weight to distortion. So you're in essence saying, okay, I'm fine with giving me more distortion, but reduce my rate. Maybe I'm in a really network constrained thing, constrained environment, reduce my rate. I'm okay with taking more distortion. And so this exactly, oops, I had actually trained it. Now I'm retraining it. But this is gonna train and this is exactly what we are going to see. While it trains, let me just come back here and talk a little bit about what are some of the benefits and issues with this learned compressor, and then we'll come back and I'll show you that part. So couple of advantages. First, there is no hand tuning of parameters. You can learn the parameters. What that means is you adaptivity which was not possible with traditional codecs, right? Your traditional codecs always had the same matrices. But now you can have, for example, custom codec for each domain. You can have like something for cartoons, something for games, something for TV series, and you can figure out different transform code values for each of them, which performs better for that particular kind of data. You can have something content aware or even task aware. So you basically get the flexibility because now you can train these end-to-end learned compressors for a specific task. The second idea is you get a better distortion model separation, which is basically says that here, my distortion could have been anything, right? As long as it's differentiable. What that means is that, so if you recall, long time back, we talked about human vision and we said MSE is not the right thing. Guess what? Like we trained something right now which was optimized for L1. I could have easily optimized for L2, but nobody is stopping us at L2 or L1. We could have basically plugged in any differentiable distortion metric, which even maybe maps human vision better or like human perception better. And actually a lot of work has gone into this and we'll try to touch a little bit on that in the next lecture, right? So you can basically completely replace distortion. Remember, this is very hard to do it in the traditional codecs because a lot of hand design decisions were made assuming you are optimizing for MSE or PSNR, right? So these are like really the main benefits of the learned image compressor. And let's just go back and see whether this finished or not. Oh, it actually finished. And now you see like reconstructions. If you look at number of bits, you get much fewer bits. Like for each of them, you're approximately getting 40 bits. So it indeed reduced the rate. But now you can see like the quality sort of deteriorated at some places, right? So like if I look at 8 and 5 here, and they were still bad, but it's better. Yeah. Another thing you see is that like these ML based compressors, they are doing a lot of low pass filtering, like smoothing, which is somewhat again we expect because it's hard to encode the high frequency components generally, right? Okay. So last thing which I just want to cover today is, so what are some of the issues? And even actually before that, okay, never mind. Okay, sorry. Let's just look at this. Yeah. So this is just a benchmark of how these compressors perform in real life. So this is a paper from 2022. Here, different colors are different compressors. The x-axis is bits per pixel, so higher value of x-axis is higher rate. The y-axis is PSNR or MSSM. Don't worry about them. These are just some metrics. Here, these are quality metrics instead of loss metrics. So higher value is better. And what you see here is like this brown curve is JPEG, this guy here, okay. This pink one is BPG, pink dashed one. So this BPG, it's this guy, okay. And there is this something called VVC VTM, which is one of the, I would say, state-of-the-art traditional codec, which is actually sitting somewhere here. I don't know if you can see it clearly, can you? Like, let's see, this dash brown. Okay, and this is like really state-of-the-art, even includes some like MLS components in the middle for like some small decision making, but this is not an end-to-end learned image compressor. It's still traditional in the sense that it still have all the traditional blocks, just uses something to learn a specific block. Versus the blue one, which you see, is what their work is, which is a learned image compressor. And you can see like in PSNR, basically it's on the most on the top left, which is what you want. You want higher quality at lower bit rate. So it's performing best. So what I'm trying to highlight is that these learned image compressors are really state of the art. Like this VVC has almost spanned 5 to 10 years of research over various components and blocks and everything and like big teams. And then now you have learned compressor which just comes and beats it. No more that optimization. So it's really cool from that perspective that given the amount of effort, the output you can get is really crazy. And this is just PSNR. MSSM is some other metric which is known to optimize, correlate better with human vision. And there the gap is even higher, right? So here you see like BPG gives you a lot of benefit. This guy gives you a little bit more and so on and so forth. A lot of these traditional codecs are optimized for PSNR, which is like MSE. Just MSE in dB scale. But MSSM, which is also, by the way, a lot of these codecs still look into, even though it's a perceptual metric, a lot of these codecs have still tried to optimize for this, not JPEG. So you can see like JPEG it's very far away. It's like this guy and all of these guys versus this blue guy is like really beating. So there's a lot of promise. So not only you can have these domain aware things, it's really at the forefront. It's state of the art. Okay, so everything is green. Why isn't there a ML based compressor everywhere? Why do we still study it like first 17 or whatever lectures of this class? Why didn't we start with this? One of the main issues with ML based encoder decoders is speed. Really, so now you have to train this, for example, in a simple example, million parameters. Whereas in DCT or in compression in general, I think really one point which we hope we have driven home is that complexity is a really big thing. Like it really makes or breaks whether something is practical, whether something will be used or not, whether something will be deployed. Because these are like ubiquitous operations, they are just running all the time. You need something efficient which can run at speed, right? So this is just like a screenshot from George Todorici's talk at CVPR 20. And what it shows here is like H266 plus enhancement is again one of the more advanced traditional codec, which is still more computationally intensive than JPEG. But this is what ML based codecs were using back then, which was like almost 20x more computational complexity. So now you can imagine, right? Like what does 20x more mean? On the surface, it just feels like, it's 20, right? But no, it's like if something was taking you 1 hour to encode decode, now it's going to take 20 hours. Something was taking you 1 minute, it's going to take 20 minutes. Now think you are working on your computer and you say, oh, this thing, 1 minute, I'll wait. This will decompress. Instead of that, now if you have to wait 20 minutes, will you use that technology? It's hard to justify that. So speed has really been one of the areas where a lot of work goes into. Don't have to worry about this. But even though this is a blocker, I think one thing which we should really take into account is that machine learning, deep neural networks have really taken world by the storm. And compression is not the only application, right? Like there are tons and tons and tons of application on your phone or your devices to apply this, right? So a lot of work has been really going on into like hardware support for neural net. And now you can think if you have hardware support for neural nets, then you can deploy all of this much more efficiently and faster on any devices you want. And this is happening not only for compression, but to enable tons of applications which are out there. Right? So this is happening anyways. And our compressors can take advantage of this sort of hardware lottery or hardware boom in this area. By the way, we have been talking about this. We are not going to touch this in the class. I don't think any team has picked up a project this time around this, but a lot of these image and video compressors, which we talked about, even traditional image and video compressors, actually have hardware support in your computers. What that means is Intel makes chip so that you can decode your images or videos efficiently on the hardware. If you were just using a commodity hardware, you wouldn't be able to actually achieve the speeds which you would like. And again, what this speeds means is whether you're gonna watch YouTube or not, whether that circle of death on YouTube or Netflix or whatever it is, whether it's going to be 1 second or whether it's going to be 1 minute. So a lot of effort goes into that. And so this is a problem which is there even in traditional compressors, but already a lot of investment and work has gone into it. And hopefully in neural nets also, we are gonna see the same. Yeah, so this is like a huge AI chip landscape, like thousands, not thousands, but like hundreds of companies working to make things better. Qualcomm, okay, this is a little bit older numbers, but basically Qualcomm has a recent chip which does extremely efficient ML inference. Today we have M3, I think, Apple chips which are doing the same. NVIDIA chips are coming out for basically doing much more efficient compression, decompression for learned stuff on GPUs. So a lot of stuff is happening in this field. So even though this is a problem right now, it's probably going to be resolved. And the second issue really is just determinism, which is something to be careful about is like different hardwares might have different floating point operation implementations, and that could lead to just catastrophic failures. Like CPU world has really come together. I think GPU world is still coming together. Every NVIDIA update, you have to be careful and what devices you are working with. So this is like really, even though this doesn't sound big, this is really important when you are working with this ML image based coders. Like whatever you are doing should be reproducible across machines and platforms. Otherwise, again, like you're not going to decode what you thought you were going to decode. Okay. And so just last slide from today and then we are done. So these are basically, I guess, the main takeaways from today. So ML based codecs, they allow you for learned encoder decoder transforms, better fidelity to chosen probability models, right? So that basically gives you the better rate distortion. So this is a point which we spent a significant time today. You can choose whatever distortion you want as long as it's differentiable. Again, very powerful because allows you to just tomorrow, if there is a better vision model, you can make a better compressor for that. Then you can have something domain adaptable and flexible. The main idea to achieve the ML based things was like just be able to differentiate across this quantization and discrete probability models. And most likely you're going to see more and more ML based codecs in your future compressors. So very hot and active area, participate in it. Cool. That's it. Thank you.